For the first talk, I'm pleased to introduce Grzegorz Banaszak from Uniwersytet im Adama Mickiewicz, who will speak about algebraic Sato-Tate and Sato-Tate conjectures. Hello, Grzegorz. Can you unmute yourself?
Thank you very much. Thank you to you, Seyon. Thank you to Victoria. Thank you for inviting. I'm happy to speak. So I share the screen. This is that. Okay. Let me just make on the. Okay. So I will talk about algebraic Sato-Tate and Sato-Tate conjectures. Can you see this? Okay.
Fine.
Very good. There'll be basically two chapters, two sections. First will be algebraic Sato-Tate and Sato-Tate conjectures for ℓ-adic representations, and the second one will be for motifs. So let me start with some history. I mean, very simple history. So we have compact topological space and Dirac measure on it, and the sequence of elements. And we say that the sequence is equidistributed with respect to the measure if the average of Dirac measures converges weakly to mu, to the measure mu, which at the bottom you have written what it means pointwise. Okay, so all right. So general notation is very simple. I have here just a prime number field and absolute Galois object that I guess everybody in this conference understands very well. So little history. I'm sorry, I will just say very basic history. I don't have time to mention it. Something very standard, so experts will not find anything here beyond they know very well. I mean, so we have elliptic curve with CM and then a prime of good reduction, take that polynomial of Frobenius, characteristic polynomial of Frobenius, so you have eigenvalues, and then they are of eigenvalues have norm QV to negative 1/2, and then you can normalize the eigenvalues as at the bottom of my screen here, and you can have element theta that is in 0 to pi, and theta v, and we are interested about these. Well, we're interested in the theta v, how they are distributed in 0 to pi, but we can look from different point of view. We can look at the matrices, diagonal matrices that look like this, 2 by 2 matrices. These are 2 by 2 matrices of this form, in general, determine uniquely the conjugation classes of SU2. And sorry, I went too fast. And we're interested how the diagonal matrices with theta v as above are distributed among all the conjugation classes of SU2. And
excuse me, Grzegorz.
Yes?
There was one ask that whether one, can you slow a little?
Oh.
Can you speak a little slowly?
Okay.
Yeah.
Okay.
There
so,
was a, yeah.
I can, but you know, you can't. Okay. So, all right. Maybe I should answer like this. I will make that presentation available. Okay. So if somebody doesn't catches anything, I mean, but okay. Let me slow it down. So then we take hard measure on SU, and this hard measure induces on the conjugation classes, so say, which are at 0 to pi, actually the same as interval 0 to pi, if a measure 2 over pi sine squared theta, probabilistic measure theta v, theta d theta, sorry. And then what we can do, well, there is what was done many years ago. There was a question by Sato-Tate, how the elements are distributed. Actually, they claim that they are equidistributed in this interval with respect to this probabilistic measure. So I would only like to finish this historical introduction with a great theorem of Taylor, Clausel, Harris, and Shepard-Barron in 2006. Actually, when K is totally real and the curve has a multiplicative reduction, some point prime sort of OK, then the Sato-Tate conjecture holds. From that point, there are many other, results about distribution of Frobenius elements, because it's basically distribution of Frobenius elements, normally Frobenius in SU2. So I'm sorry, but I will not say more about this history because I have many other things to say. So I'm sorry. Let's go to my talk. Maybe at the very bottom, I should add that Sato-Tate conjecture is known also for CM elliptic curves. So what I'm going to talk, so I will talk about ℓ-adic representations such that when they are related to Hodge structures, so of course, not every Hodge structure can write ℓ-adic representation, but we'll talk about Hodge ℓ-adic representations that are related to Hodge structures. But let's talk first about Hodge structures. I will talk about pure polarized rational Hodge structures of weight n, polarization, pairing, and then we have Hodge decomposition. The example is the singular cohomology of a smooth projected variety of an amber field here, rational cohomology. And let's define, so when you have this pairing, as you see here in second line, you can define groups, simulated groups, but when you have the pairing, when you apply G, a matrix from GL, so group scheme GLV, you have that property, and then isometry of a form, a polarization form, and then this, of course, gives a character, which is just sending G to chi G. So you can see that this iso group is just simply kernel of this character. So this first line, when you see at the top, defines together the group and the character. In this way, you can see this. Let's consider, so please look at that. Let's consider co-character from GMC to, which is C cross to GLV. So when you make a complexify the V space, then consider the character defined as follows. So recall the Hodge decomposition of the first page of here, third line. Then define the co-character on complex points in the following way, that Z is sent to Z to negative P on the factor of the summand VPQ of the VC. Then the Mumford-Tate group is the smallest algebraic group, but its definition of a Q such that the Mumford-Tate complex points contain the image of the co-character. And Hodge group is a connected component of the intersection we defined as here like this. So the intersection with ISO, or the Mumford-Tate with ISO. This DH, we call it decomposed Hodge. So you can see that's the how we write it. And then maybe from the very beginning, let me introduce a parity group. So Betty parity, so we define with Kiran this group. And you will see a number of these groups today. It will be ℓ-adic, Betty, one, and motivic. So the parity group has the following property, that this is just a group of at most 2 elements. So this plus minus 1. The first proposition. Second one is when n is odd, the weight is odd, then the parity group is trivial. It takes a little bit of computations. When n is even, but dimension is odd, then the parity group is non-trivial. So you can see a little proof. So the ISO is here, in this case, when n is even, is orthogonal group. Then the Hodge is, of course, contained in ISO. And it is just orthogonal, this plus minus identity times SLV. So negative identity doesn't belong to Hodge because determinant, remember that V is odd, the dimension of V is odd, so the determinant is -1, and Hodge is connected, so if it belonged, then of course Hodge would be disconnected. So that's a simple proof of non-triviality of this parity group. Example, you have abelian threefold, so take V equals H2 of this threefold. It has weight 2 and dimension 15. So So that is non-trivial. Okay, so that's simple example, one of the smallest examples. In general, we go for Lefschetz group. So Lefschetz group, so take a subring of endomorphisms, but of Q linear endomorphisms that preserve Hodge decomposition when you complexify the space. Sorry. So the Mumford-Tate you can readily find out where it's contained in centralizer of D in this group, G iso, and the connected component, of course. And the Lefschetz group is known for many years. It's defined as follows. It says as centralizer of the in the iso and connected components. So that's the Lefschetz. So we go for this one of the first observations with Kiran to go for algebraic Sato-Tate. We can have to extend it. So take this. I mean, take something bigger than L, because when you work with Sato-Tate, there is a question of connected components. So we realized. So we wanted to find some bound from above for algebraic Sato-Tate group, which was still yet at some conjectural, still is conjectural. So, but find something that will be very close to algebraic Sato-Tate. So hence, from this definition, we get immediately that Hodge is contained, of course, in Lefschetz. And let's go to definition. So we assume that D, this is assumption, okay? So this is assumption. For motives, D will be given and will have, of course, this property. So imagine, so you can think about abelian variety and a ring of endomorphisms, K-bar endomorphisms. Of course, you have this property. So you can think like this. So here, it is general setup. So we just assume it, but it has a continuous representation. Actually, discrete is discrete because it is D is just a finite dimensional vector space. So take this representation coming from this assumption, and then you can have KE, the field, fixed points of a kernel. So this Galois extension of K. And we have, for each tau that belongs to this group, we define a closed subscheme of iso, a closed subscheme, which is just simply defined in this way. So we just take all G's that conjugation with beta gives you image of rho E of tau acting on beta, okay? Because it is via this homomorphism. So, and then even further, we go define the decomposable Lefschetz. It is people who have read our papers and other papers also use this. So remember this very well. We have this group. This is a group actually. So when you multiply, that's interesting. But when you multiply just group multiplication in this iso, because it is subgroup of iso, when you multiply d tau, dlk tau times dlk tau prime, you will end up in dlk tau times tau prime. So it's very nice. So it's nicely, and actually you realize that the dlk identity is just that centralized of iso. And then Lefschetz is simply, of course, oh, sorry, what's going on here? It's simply the connected component. Corollary here is just when, well, you can, it's not difficult to prove. When Hodge is explained by endomorphism, so when Hodge is the CD iso, then parity group is trivial, but there you can, it's not difficult to prove. Okay, the point, maybe the point is, immediate point is that iso contains identity, negative identity, and CD is also, it commutes with D. Identity commutes with D, and actions, of course, it's the proof is trivial. There is the following natural monomorphism. Actually, we don't know if in this general set in some of the subgroups, but there's also subschemes, this D tau may be empty. These are just subschemes. They are not subgroups. They are subschemes. The only subgroup is when you have tau equal identity. So, so what we have only an embedding of this group, of these groups. So now that's everything about Betty, about Hodge. We just go to, well, I have ℓ-adic representation associated with Hodge structure. I said we just take QL space, just tensor in the V psi, the Hodge structure. But it is, we assume now, it is important, we assume, okay, we assume that it has the GK arcs on this. So this is like you have a ℓ-adic realization of a motive, right? And you have a Betty realization when you, this is all we will see later on for motivic thing. But here we just assume it, but it's still very general thing. Just assume it that it happened that V is such that V psi is such that when you tensor with QL, you get just ℓ-adic space, ℓ-adic bilinear space. And then define, well, out of this you get ℓ-adic representation. And we will assume about this that this is Hodge-Tate type and strictly compatible in the sense of Serre. Okay? That is, as in the book of Serre, abelian representations and elliptic curves. So then you have clearly stated what is strictly compatible. Simply means that Frobenius elements do not, I mean, they are the same, whatever L you take. I mean, and then, yeah. Example, of course, is, as I always, dark homology, algebraic closure. Extending coefficient algebraic closure. Okay, so we assume additional thing that is often that the Frobenius absolute values, again, values of Frobenius on this VL space have absolute values QV2 negative n over 2. So all the eigenvalues are just like this. Okay, so this is like, say, for abelian variety, n is 1. Okay, and so we'll work with such objects. Okay. When you have cyclotomic characters, we assumed, I'm sorry, let me return here, did I write here? So I should have said here that, we also assume that this psi L is GK equivariant. Okay, because of this equivariance, there is then you have a Tate module on the target of this psi L. So it says that this GK equivariance brings you this equality, just of the equivariance. Okay, let's go further. So then it's classically what you do then, just take this image of Galois. It is in the GISO as by its definition. So take its Zariski closure. And then what we do, we define the intersection of the Zariski closure with ISO. Now ℓ-adic, ISO of this ℓ-adic space, bilinear space. Define this, and then see what, by Bogomolov theorem, because now you have a Hodge-Tate assumption. This Hodge-Tate assumption gives you the property that the Bogomolov, theorem of Bogomolov, which says that there are enough homotheties, so that contains also this GLKR contains homotheties, and you have immediately exact sequence like this because of the homotheties. So on the right you have chi's going to GM. Now what we want to do, we want to twist. So you remember how we constructed this group DL. DL was constructed somehow by putting together the pieces DL, K, tau. But now you can twist our groups by tau, we defined here. So you can see that GLK tau is just similarly, but this is just a subscheme, okay, of GLK arc. The same is will be for GLK arc 1, so also twisted, just taking the intersection. And then there is nice lemma that the GLK arc and GLK arc 1, they are just simply disjoint sums of these subsets. Of course, when tau is 1, this twisted for identity are just a subgroup. But it is interesting that you can simply prove here that actually you can prove even more. I mean, I'm not it is proven in the second paper, contemporary with Kiran of the conference in Lumini. This was proceedings from Lumini, that these actually are cosets. So there are cosets of this GLK arc identity in this GLK arc. So you have, well, it takes some it is not obvious, but it is not very big. And what we have here, we can prove, you remember the twists of DLK twists, what we did find actually very nice. You can find that this twist of GLK1 arc tau is contained in GLK tau, DLK tau, and the same for, and then of course, because of this, you get the GLK arc is contained in the full DLK. So now we have some upper bound. I would say one thing, maybe I should say at this moment, that this GLK group is very important because it contains the normalized Frobenius element. So you remember this when we discussed at the very beginning of the history. So the equidistribution was a question about distribution of normalized Frobenius elements and normalized eigenvectors. So here will be this GLK1 arc. It's, for this reason, it's important that it contains the normalized Frobenius elements. Okay, so going towards equidistribution. Now you remember that this group in the middle, going to the right, was only embedded, but somehow when you introduce this, when you force V to be related to this this ℓ-adic space, you can prove that actually this DLK of a DLK identity is isomorphic to GLK E. So there are no empty DLK taus, simply because of this. So this is interesting, but this in this general setting you can find out that how Galois theory simply gives you information about this object that come from Hodge structure from, let's say, transcendental theory. Okay, going further, consider natural homomorphism, coming of course from that ℓ-adic representation. So it's simply embedded into GLK arc QL points, and then take connected component of this GLK arc, and then take QL points and take pro-image back to Galois, and then you will see, because there's a connected component group of GLK arc, say the algebraic group, yes. Connected component is a finite index. Then you have this pro-image is a Galois group. And the Galois group simply, the Galois group, absolute Galois group of a base field here is K0. So there's this finite extension, what we have here, K0 over K. And then what we observe that K over K0 is the minimal extension such that GLK0 arc is GLK arc connected component. When n is odd, it follows that K0 is the minimal extension such that not only GLK 0 is connected component, but also GLK 01 is connected component. In principle, of course, K0 may depend on that. There is an exact sequence, of course, that you can prove that exactly. I mean, this exactness of the sequence I usually made it to diagrams, but today I will not put it. And then the kernel is a group, GLK0 modulo, divided by connected component of GLK arc, of course. It contains this connected component of identity in GLK1 arc. And this is isomorphism, of course, even only if GLK01 arc is connected. So define ℓ-adic parity group to be this group. And it is a component group of GLK01 arc. And what is interesting, but if n is odd, you can, of course, prove it was n. So for n odd, this paper, I mean, so this is paper in progress with Kiran, so we can consider here not only odd case, the odd case was done in the paper we had in proceedings of the mini conference 2014. So when n is odd, you can, let me see, so you can, oh, sorry, it's something, yeah. Oh, so when n is odd, or when GLK1 connected component is just the CD of ISO, then PV psi L is trivial. Okay, when n is even, then in dimensional, then in the same way as for the transcendental, I mean, for the parity group, Hodge, Betty parity group, you can prove that PV psi L is non-trivial, kind of the same proof. Okay. Example again, take the abelian threefold that we used before, and then you see that this ℓ-adic space is again will have has the property that it has dimension 15, so has dimension 15, and is of course yeah, that's the n is odd because n is even because this is wait, I mean n is 2 here, and space has dimension 15, so the group is non-trivial. Okay, that is another theorem that we haven't had before, even for odd case. So we were able to prove it now. I mean, sorry, wait a minute. So when you assume that K0 with this field, K0 mu L bar is L when L is bigger than 2, and L bar is 8 when L is equal to 2, when these fields don't intersect, and when you have enough homotheties in a GLK, rho L GK, so in the image of Galois, we have enough homotheties. And when the parity group is trivial, ℓ-adic parity group is trivial, then you can prove that this that GLK1 arc is actually is Zariski closure of this group. I didn't define it here. Rho L GK1. What is this rho L GK1? These are all points of rho L GK that are contained in this GLK1 arc. Okay? So because the rho L GK goes to GLK arc, so rho L GK1 is these are all images of Galois that are in GLK1 arc, and then Zariski closure it turns out to be GLK1 arc. Okay. Okay, so let's go for algebraic Sato-Tate conjecture. So let me just write it. So for every number field, there exists a natural, so it's stated that every number field, there is natural in K a reductive algebraic group, AST KV psi, contained in ISO. The group is of course of a Q, and natural, it is natural in K, so when you extend the field, the group may become smaller, okay, but it is some diagram, of course, naturally will commute, such that you have embedding, so there is a map, natural map that is an embedding for every L, and and as point B, the difficult part is that the maps should be isomorphisms. So simply you can organize these GLK1 arcs for each L. Somehow they there is object, this ASTK V psi, that remembers somehow, it is, even though it is group of a Q, some algebraic group of a Q, it remembers when you extend coefficient to QL, you get you back this GLK1 arc. So that's a property that we know from something like this happens in Mumford-Tate conjecture. We're also heading for this. Okay, and then currently, see, this is work in progress. I'm sorry, this is just, we currently consider this under assumption that this parity group is trivial. So we just don't claim it in the full generality as we have here, but currently it is for this, by this assumption. When you assume Sato-Tate conjecture, you can take that as we denote semi-simple part of the normalized Frobenius. Okay, as I said, it's the GLK1 arc C with this isomorphic by this AST complex points, and the conjugacy you can. So in conjugation class of these elements of complex have complex absolute values 1, and they there are some conjugate that is contained in a maximal compact in this the complex points of AST group, a maximal compact, and this allows us to make the following conjecture. So we can always navigate this SV by conjugation to this compact subgroup ST. By the way, this ST will be called here Sato-Tate group. The conjugation classes of the Sato-Tate conjecture, in this very general form, says the conjugation classes of these SVs in this STV psi are equidistributed in the conjugation classes of this group, and conjugation classes of this group. So conjugation class again of these chosen elements of normal Frobenius elements are in conjugation classes equidistributed in the conjugation class of this ST V psi. So this is a compact space. ST is just compact group, and then conjugation class of compact space. And it is with respect to that Haar measure induced on this conjugation of ST K V psi. When we take a proposition, so when we assume it's Sato-Tate, algebraic Sato-Tate conjecture, previous one AST conjecture, then there are natural isomorphisms. So you can see that the first one, the component group of identity of GLK1 arc is this pi 0, it's the same as pi 0 as AST KV psi, but the group on the right, this pi 0 is topological one. This is pi 0 of a compact topological group, compact Lie group, actually. And then, so what I wanted to say, there is a theorem, you can prove it. Again, you remember, you see that the assumptions that appear already in the theorem about closure rho KG1, the same assumptions, except the third one is just the AST, I mean, so we assume here Sato-Tate, algebraic Sato-Tate conjecture, then you can write algebraic Sato-Tate group. You can write algebraic Sato-Tate group as when you extend coefficients as the joint sum of these cosets, and the same happens for Sato-Tate group. The same happens here. Because of these assumptions, three assumptions are important, especially one, second one. So you can find these rho 1 tildes that run of a set of coset representatives of GK0 and GK, but with property that the rho L of them, of sigma tilde, is in rho L of GK1. So this is important. So the assumptions are basically important for this. So you can find such a coset representatives. And then this is well, this theorem is it takes a number of pages. It is one maybe most difficult theorems in our paper. in progress. So under assumptions of the above theorem, the Sato-Tate conjecture holds for the representation of L with respect to this Sato-Tate group that we've seen above. If and only if for each sub-extension K1 of K0K, for which K0 of K is cyclic, the Sato-Tate conjecture holds for the representation of L restricted to GK1 with respect to, of course, the Sato-Tate group for K1. Yeah, so this is actually kind of, you may feel something like Brouwer induction or something like this in it. There is a trick, actually, in the proof of this theorem, we use a trick that was used by Taylor et al. For the proof of potential automorphy. So this theorem is quite difficult to prove, but it's nice. Okay, let's see. We go to conjecture Mumford-Tate, which says that for any Mumford-Tate group, remember, was defined at the very beginning for any prime number L, that connected component of GLK arc is just Mumford-Tate group. Let's look at abelian varieties, because it is a standard case. Okay, let's see, that was okay. Recall that Deligne, Boroboy, and Piatowski-Shapiro independently proved that for any prime number, this GLK connected component is contained in Mumford-Tate group. This theorem is equivalent to the following inclusion. When you take GLK1 connected component, it is contained in Hodge group. Okay. And conjecture Mumford-Tate can be here written in this way. Before, on the previous page, you've seen this very general statement. This is a classic one here, of course. And then it is equivalent to the following equality. And so this Mumford-Tate is equivalent, Mumford-Tate conjecture is equivalent to that equality. GLK1 connected component is Hodge, with coefficients extended to QL. And then, so we prove that this actually, this was the very beginning of our cooperation with Kiran, maybe kind of proven the first day we met. And well, vaguely, that if Mumford-Tate conjecture holds for A, and K is such that the GLK arc is connected, then the algebraic Sato-Tate conjecture holds for A, with algebraic Sato-Tate being just Hodge group. But then you, of course, have to extend field, K, so it's not for every K but yeah, it was nice observation. We started with this observation. Nowadays, we have much more. So Victoria with Jonathan, Kamalin, Victoria proved that the following theorem, that for abelian varieties, the Mumford-Tate conjecture implies the algebraic Sato-Tate conjecture. And so for abelian varieties, so yeah, that is the theorem. Let's go further. So recall that, well, if you recall that in special, this group DLK for abelian varieties is written in a shorter way. So recall that we had this equality. It was even for all Hodge structure, and the ℓ-adic representation related to them. So not for, well, for all ℓ-adic representations, the other way, related to Hodge structures, as we had at the very beginning. So we had this inequality. So with Kiran, Kiran was working with Fite, Sutherland, and Roger, and they needed some result of this sort for classification of Sato-Tate groups for abelian surfaces. So here we observe that when you take, when Hodge is just Lefschetz, and Mumford-Tate holds, and the DLF is connected, then you have actually Sato-Tate, algebraic Sato-Tate conjecture, with this DLK group to be the algebraic Sato-Tate group. And this was also from the very beginning of our cooperation. And if you look at the algebraic Sato-Tate conjecture, yeah. So for this reason, of course, we have AST of A is DLKA. Let's go to the next slide. For abelian variety of CM type, Hodge is equal to Lefschetz, and and then DLF bar A is connected. So then, of course, algebraic Sato-Tate conjecture holds for CM abelian varieties with ASTK, A equal DLK. The same for abelian varieties absolutely simple of dimension G, which endomorphic algebras of type 1 in algebraic classification, etc. With these assumptions, algebraic Sato-Tate conjecture also holds. And then for abelian varieties of dimension at most 3, you have a similar situation because it happens because Mumford-Tate conjecture was proven by Paulman. Mumford-Tate conjectures for abelian varieties of type 1, 2, and 3.
So there was a question, sorry,
yes,
Grzegorz. I can try to unmute Jacob.
Yes,
I can't find the name though. Victoria, can you find someone who raised a hand? Oh.
Can the person raise his hand again eventually?
No, I can't find it anymore.
okay,
No.
let's go.
Yeah, sorry.
Okay, so Mumford-Tate conjecture for abelian for families, I don't describe them, was proven by myself, Wojciech Gaid and Piotr Krasoń, independently by Adrian Basiu, but it was for families. I'm not specific here, just and Mumford-Tate conjecture for abelian varieties of dimension less or equal than 3 was, I mean, very many people contributed here. Jean-Pierre Serre, he, Imai, Hazama, and probably other people. I'm sorry for if I didn't quote anybody else, which I missed here. I'm very sorry. Let's go further. There are no Sato-Tate groups. We have 3 types Sato-Tate groups for elliptic curves. So you see that SU2 for groups elliptic curves without CM, S for CM defined, CM type defined of a K is just UAM, and CM not defined of a K is just a state. It's been normalized, and Sato-Tate is normalized of U1 as U2. That was known. It is classical history. However, by Francesc, Vitek, Kiran Kedlaya, I mean 2 speakers also here, together with Roger and Sutherland, proved that found that all possible types of Sato-Tate groups for abelian surfaces, and very recent work for they listed all Sato-Tate groups, the work in progress, all Sato-Tate group types for abelian threefolds. So I had some S. Okay, so this is a theorem that there are 52, exactly 52 up to conjugation USP4, which occur as Sato-Tate groups for suitable A and K, on which 34 can occur over for K equal to Q. So this is the theorem from 2012, actually, that they were used a little bit our results with Kiran. And then a new paper, I just seen that a few months ago, when you have a threefold, then there are 410 groups up to conjugation SUSP6, which occur as Sato-Tate for suitable A and K. Okay, so I should add that Christian Johansson proved some cases for Sato-Tate conjecture for abelian surfaces. So that's his theorem on transactions. We have, I'm sorry, this is also just not very precise statement because he had very technical paper. So the Sato-Tate conjecture holds for many cases of Sato-Tate groups listed by Vitek, Kedlaya, Roger, and Sutherland, except in the case, the generic case, the USP4 was not resolved in the work of Christian Johansson. So okay, so now we finish here the algebraic Sato-Tate conjecture and Sato-Tate conjecture discussion for ℓ-adic representations. Now let's go for motives. So in my case, I will consider motivic category either Deligne motivic category for absolute Hodge cycles or André motivic category for motivated cycles. So that will be a category when you take a motive. So tilde here, tilde means either motivated or absolute Hodge. Let n tilde m, when you take a motif, will be a subcategory, Tanakian subcategory, smallest Tanakian subcategory containing m. And when you take fixed embedding, we take a Betty, fiber functor, and is related to this embedding. And let V be the, well, denote the HB of M. Okay, so that the vector space that is assigned by this fiber functor. And then GM tilde will be the automorphic group of this fiber functor. Sorry, so motivic Galois group in other words. And then GM tilde M is this, of course, restrict the fiber functor to the subcategory, subcategory. So this is that subgroup. Then D is here that when you extend coefficients, consider the motivic category of M K bar, you have let D be feathering. And let's, so this is because it is, these are semi-simple categories. So this is finite dimensional Q vector space is D. And HD is, it has, of course, action of Galois. So H0D is, let denote the Artin motive corresponding to D. So this Artin, well, so H0 is the Artin motive corresponding to D, to this Galois representation. And M0D, let be the smallest Tanakian subcategory of this M tilde 0 of this of these Artin motives. Actually, I'm sorry, I should have written here Artin motives. Here should be K, M0K, but because Artin motives in all categories are the same, and motivic categories are the same. So, so we take the smallest Tanakian subcategory containing that motive. So this is the smallest Tanakian subcategory Artin motives. And put, of course, the Galois, motivic Galois for this category. And then you have that thing. So that group is actually, as a group, algebraic group is just a Galois group, finite group. Very nice, that relates to the previous we had. And then also you can twist these Galois groups as similar as the DLK, and twist them. And observe that, again, as we twisted this algebraic Zariski closures, this is also, they come, the GM, the Galois group come as disjoint sum of the twists. And the same will happen for GM1. Remember that GM1 is just here, defined as GM tilde M intersected with ISO. So we have corollary. The corollary also holds here as above and with theorem above. And what we have first theorem, the group scheme is reductive and very short exact sequence. You can see very similar to the ℓ-adic exact sequence. In particular, this group G, GM tilde. Let me see, did I? What is this GM tilde M1? It is the intersection, of course, of ISO with GM. Did I have this group here? Okay, okay, yeah. So this is the intersection with ISO of this GM of M, intersection with ISO, and then it contains, of course, the connected component of this intersection. And you have the zigzag sequence, but in particular, in this group GM tilde M1 with this 0. I mean, this little 0 above doesn't mean that this connected component is always contained in I mean, I write in parentheses and outside. So this is not, this G0 M tilde M1 is not necessarily connected. And you can prove that, you can prove this theorem by looking at this diagram. Because the proof is done by this by looking at this diagram. You can see that the exact sequence above and the previous slide on this slide is just the right column of this diagram. Okay. So, oh yeah, so sorry. So this is, so yeah, okay. let's go. So define a parity group. Actually, the parity group, it is the imperfection to be IM being isomorphic. So this would be the parity group. Is defined as follows. And then you can prove again when n is odd, or if this parity group comes from endomorphism, then of this iso, then the Hodge is, in particular, the Hodge is coming from, Hodge group is coming from endomorphism, then this PM tilde, psi tilde is trivial. That's very similar to the ℓ-adic and ℓ-adic case. And n is even and dimension is odd, then again you can prove that P, this group is non-trivial. Well, again, for it holds, the example is again the same abelian threefold. So this is what you've seen before. Okay. So the motive here is H2 of A. What is the following property? Again, but this GLK1 arc is contained in this Galois group. Here I see I forgot to, instead of K should be tilde, but all right. Motivic Mumford-Tate and motivic Serre groups are defined in the following way. And Jean-Pierre Serre conjectured that connected component Mumford-Tate, motivic Mumford-Tate is just Mumford-Tate group. And you can see that when some abelian varieties, you can, of type 1 and 2, you can prove this. But it's for type 3, some assumptions also true, but on this very right, the CD, you have to take connected components. So I just wrote it in this way because these equalities also hold here for abelian varieties of dimension at most 3. So I didn't mention here type 3 abelian varieties. So you see that this Hodge is connected to another motivic Serre group, and MTA Mumford-Tate is of motivic Mumford-Tate connected component. Algebraic Sato-Tate group is defined as follows. So, well, this is Serre actually. This is Serre with this proceeding of symposia and 55. So we just follow directly. This is following directly Serre. So this definition should be attributed to Serre, of course. So this absolute, I mean, this algebraic Sato-Tate group is motivic Serre group by definition, and every maximal compact subgroup will be called a Sato-Tate group associated with M, and will be denoted STK. So I write here, I don't. So we don't write here this tilde when you define STK and ST. Because it is important, this group is important, it depends in a very important way on that field. So what are the basic properties what we basically prove on the way here? So that STK, what takes some time is in this, again in this DLK, where V is this Bettier realization of motive. Hodge is contained in algebraic Sato-Tate. Well, we don't. I mean, we don't know the dimension. This you may be surprised by this, but we don't know if Hodge has the same dimension as algebraic Sato-Tate. So simply, it is only containment. When you assume that Serre conjecture that you've seen a few slides before, then this is equality. And you see that the pi 0 of algebraic Sato-Tate here is the same as pi 0 of motivic Mumford-Tate, even only if actually the identity V belongs to, minus identity belongs to AST, connected component. Also, the connected pi 0 of AST is just pi 0 of ST. And you have the first part of this algebraic Sato-Tate conjecture here, that this GLK1 arc is contained in this AST. So this, I mean, this very nice to see that this definition of Serre of this algebraic Sato-Tate group is, I mean, has very nice properties. So you can see them here.
Grzegorz,
And
can I remind you that it's 5:22?
yeah, so I'm finishing. So I'm finishing. So this is from theorem. You remember that was for ℓ-adic situation. We had this theorem about. Yeah, I'll finish in 2 minutes. I'm sorry about this. So when you take the motive ℓ-m, and take standard assumption, then the suffix of sorted condition rho L with the Sato-Tate of n of a k even only if for every sub-extension k1 such that k0 by k1 is cyclic, it holds for GL for a restriction to GLK1 with respect to Sato-Tate 1. There's a remark that you can take motives that are just factors of this the motive you've seen here, but for categories we don't know, ℓ-adic realization gives you a strictly compatible family, so you need to assume it. And last, I guess, last 2 slides, we assume that Hodge is just coming from endomorphism, then you can determine this algebraic Sato-Tate as connected components left-sheds. Pi0 is this Galois group, and ASTM is this DLK group. So it's quite generous. You can see that the algebraic Sato-Tate is very, very well defined here. This is, recalls the previous one. And the same here for when you in addition drop in Mumford-Tate conjecture to the assumptions, then you have, of course, what we've seen before, then you have Sato-Tate conjecture holds. Actually, Mumford-Tate conjecture implies Mumford-Tate conjecture implies algebraic Sato-Tate conjecture. So, but in addition here you have this algebraic Sato-Tate is just DLK. So here at the end I listed the. Sorry, this is far away from any full list of references, but I listed references are very, very important for this presentation. So there's last page, and thank you very much. That's all I wanted to say. Let me stop here. Sorry for taking 4 moments.
No worries.
Well, thank you very much, Grzegorz Banaszak. Should we thank to Grzegorz first?
I stop. Well, I will not stop sharing because there will be questions. So let me just thank you very much.
Yeah, so indeed there are questions.
Yes,
let me first allow people to talk.
Yes, sure.
So could, if you have questions, could you raise your hand?
So there was a previous question as well from Mark. So Mark, perhaps you can ask the question.
Okay, yes, sure. Yes, please.
You can unmute yourself.
Excuse me?
Yes, perfect.
Now you hear me. Yes, that was your comment on the. I was a bit surprised. I wasn't sure. Abelian varieties of CM types. You said
Yes.
that the left-sheds group is always the same as the Mumford-Tate group.
Yeah, I'm sorry. This is. I am not at this moment. I cannot. Mumford.
That
No,
is when you write.
as a Hodge group. Yes, a Hodge group. You say, aha, because you're talking about Hodge. Yeah. I wouldn't, you know. I would have to look at the paper. There may be some additional assumption. It is just, as you remember, I was talking about kind of.
I would have. I can't answer. I'm really asking the question. I don't know the answer right away. But I'm under the impression that it's true if the sort of the torus is of because Mumford-Tate or Hodge is a torus. If it's of maximal dimension. And if it's of smaller dimension,
So you say that this so-called non-degenerate or something like that, right?
Yes.
Okay, yes. Yeah, you are right. Maybe I was a little bit vague in the statements of it, but I'm sorry about this. I didn't quote. So you are right that this is
just a minor question.
no, but thank you very much. Actually, there was a paper by me, Wojciech Gajd and Piotr Krasen. Well, I mean, Piotr, as I can say, is here. Then we work on this non-degenerate CM abelian varieties, and then of course we computed this Manford. But Polman, of course, got the Manford. But you are right. Computation of Lefschetz is a delicate thing. So yeah.
I would have a tendency to think that, in some sense, the dimension of the Lefschetz group will only depend on the dimension on the abelian variety. In that case, yeah, I'm wrong. But
this is only for because the Lefschetz is just this Betty thing, right? And so.
Okay, so if that is true, then okay, the dimension of the Manford-Tate group does depend on the CM type. I mean, if the CM type is non-degenerate, then they match. Yeah. Otherwise, it would be smaller. That's why I was worried. But
okay, yeah, thank you, Mark. Yes, sure.
Yeah, just to comment, I think that is a real issue. So I think that the basic example, the basic interesting example, is this four-dimensional example by Shiota, where you see an exceptional Hodge class, and so this gives you a case where you actually see the difference between Manford-Tate and Hodge using an SCM in the CM case.
Okay. Further questions?
Yeah, so there was a participant who asked earlier, I think that Kiran answered as well during the chat, but he was wondering if there is a relation between the Betty parity group and the Betty numbers. So that was Deligne.
So the Betty I call, how to say it, Betty we call it Betty because it is just related to the Betty realization, but let me see. Oh no, well, we have
the comment I made when this came up is you had a slide stating the theorem about when n is even and the dimension is odd.
Yeah.
So if you could put that slide back up, that's a partial answer to this question.
Yeah, let me go to this. Okay, sorry. No, back. This very beginning of this.
Yeah.
Okay.
This one. That middle proposition is some kind of partial answer to this question.
Yeah. Okay.
So if the Betty number is odd, then this parity group is.
Oh yeah. Oh, sorry. Yeah. Yeah. Okay. Yeah. Yeah. Sure.
I think that was part of the spirit of the question.
Mm-hmm. Are there any further questions? I'll be happy to answer.
I think it's probably better to move on to the next speaker then. Well, thank you very much first for giving the wonderful talk.